data as much as possible. Each of these straight lines is essentially a principal component, and there are as many principal components as there are variables. So if you have 200 variables, you could potentially have bquant and machine learning. In this webinar, we'll be focusing on principal component analysis, or PCA. My name is Christian Contino, and I'm from the Sydney Desktop Build Group. So what I would like to cover in this session is understanding what PCA and what are its uses, essentially what is it for. Maybe give a simple interpretation without using any mathematics at all, actually something that's a little bit more intuitive. Then we'll look at actually downloading some data in bquant and applying this to our local market, the ASX 200. Maybe trying to create some factor returns using PCA, so something a little bit more practical, and then a quick conclusion. And there, I'll try to keep this under 15 minutes. So let's just move to bquant. All right, fantastic. So PCA, what is it for? I think there's really two areas where people try to use it for. One is to try and condense information, especially when you've got a very large number of original variable. And the idea is also that you have minimal information loss. So in this case, when you have a very large universe, maybe potentially hundreds or thousands of stocks, you can't realistically model or use all of those, and maybe something like some of the models that you can use, like time series analysis, it would be just too much. So how do we reduce this in a way that the information isn't lost that much? Secondly, is try to discover some sort of hidden features which are not immediately intuitive. I think this is quite useful in the sense that there might be some sort of mathematical or statistical structures which might not be immediately useful. I think both of these cases, they are really a conduit, or really PCA is really an intermediate step in doing sort of further analysis, in where otherwise you'd have too many. The number of input variables would be too large, and so you can actually reduce this down and actually feed it into something else, which will actually be what we will do in the third module following this. So a bit more of a layman explanation without boring anyone with sort of mathematics. The way I like to think about it, PCA is just about fitting straight lines through a set of data points. We can all sort of imagine that. We just sort of have a scatter plot, and we think, okay, well, what is a straight line that really would represent this data as much as possible? Each of these straight lines is essentially a principal component, and there are as many principal components as there are variables. So if you have 200 variables, you could potentially have 200 PCAs. So the first PCA, the most important one really, is really a best fit line through the data. So we can all sort of imagine that, like the scatter plot that we've got there. How do we fit a line through that? So it's really a simple sort of regression line. The second PCA is actually the best line that you can fit to the errors of the first principal component. So in terms of where would that line actually go? If we think of as the sort of black rotating line as the principal component, we want to get to the point where the variance, which in this case is sort of like sort of the spread of the data, and here we can sort of think of it as how spread out those red dots are. If you look at the animation, they start to get more and more bunched up as the line sort of approaches, maybe at the vertical, they're really bunched up, and then they start to spread out more and more, and that's where the variance is actually maximized. The second part is actually the straight red lines that go from the blue dots to the red dots, and that's really your errors. And what we're trying to do is actually minimize the length of the square of those red lines. When those two are actually reached, which will actually happen at the same time, that is our sort of that is where the principal component is or lies, or when that line is. In this case, you would see those sort of purple ticks at the extremes, and that's where we would actually place our sort of PCA. Pretty interesting animation. I actually took it from Stack Exchange. I can't take ownership for that one. Let's actually dive in and look at sort of the ASX 200 and how we can apply PCA to this. So just firing up straight into some BQL code. So this is literally just getting the universe, setting it to the ASX 200, and saying that my for the last 2 years, I want to look at the sort of day-to-day total return. So that's just your period-on-period return, and that's all I'm going to do is just try and see what that data frame looks like. And it is 200 columns long, so it is the ASX 200, and these sort of look like daily returns. So I've actually picked the right field. I'm doing the right thing. So I'm just to even a bit more visual interpretation, just sort of what do these the cumulative returns of these stocks look like. So let's pick a couple of names that we're familiar with. I'm going to pick maybe rt2 Milk, and obviously it's done very well over the past few years. Maybe a bit of Wesfarmers, and really that's what we're trying to do, is trying to understand, okay, well, is there some sort of commonality between these stocks that we can try and extract? And this is what we'll try and do with PCA. We won't be applying it directly to a cumulative series like this, or the prices are directly. We'll actually be doing it on the correlation matrix, and that's very handy that Pandas has just a one command .core, and that just gives me a correlation matrix really nice and quick. Here I'm just going to extract the stock names, and this part is where I do the PCA. So I'm just going to zoom in a second here, right? So I'm actually just doing the PCA here, and actually I can pick how many components I actually want to see. The reason why will become clear in just a second, why I might want to limit them, but let's just say I want to pick just the 3, right? So I'm just going to pick 3 components. This is my PCA function, which I've imported it from sklearn. It has very simple sort of decomposition section, one for sort of PCA. Fantastic. And then I'm going to say PCA, fit it to the correlation matrix, and save everything into these sort of principal components. Then I'm just going to apply some labels. So this is, I'm just going to put everything into a data frame, and this is really what it looks like. This is the output of it. We have these PCAs, and they start counting these principal components, and they start counting at 0. And then I have these values here. All right, so maybe let's just plot them. Actually, let's just plot something else. So what we're actually plotting here, I'll go back to this table in just a second. So what we're actually plotting here is what we call sort of the eigenvalues, or sort of the cumulative eigenvalues. I promise I wouldn't go too deep into sort of any mathematics, but really what we're seeing here is for those principal components, 0, 1, 2, how much of the variance, or how much sort of the returns are they actually explaining. So it's just saying, look, if I just pick principal component 1, if I fit that first straight line through all my dots, I can explain about 54% of the variance. Cumulatively, if I add principal component 0 and 1, I can go to 65, and then I can go to sort of 71, and so on and so forth. If I did all 200 components, because that's how many data items I have, I would eventually reach 200. Most people tend to stop when they reach around 0, when they reach around 0.8 or sort of 80% in terms of variance, or you could potentially stop when you reached a number. You can fix your number of principal components that actually suits your model. If we actually look at this little plot here, which is actually just an interpretation of this chart up here, this is actually the strength for each stock to that component, right? So we can actually see most components have an association to it. Whether it's positive or negative, that it's sort of irrelevant, sort of mathematically, but you can see sort of there's actually only a handful of stocks which have a positive, in this case, association to it. The majority of them actually have a negative value, and this is what this table is showing us. For each stock, what is the sort of the strength of the relationship to each of, or the contribution to each of these principal components. So we can see A2 milk, it's positive here, negative, and then very sort of slightly sort of positive. And you can do that for each stock, right? So if you sort of look at, this is the sort of PCA 0, and interestingly, let's have a look at which stocks have a positive association, right? So it's actually only a handful. There's quite a few tickers. I'm not a ticker dictionary, so all I'm going to do is do another BQL request to actually download the names. And having a quick look through these names, it looks like the majority of them, like you've got mining, resources, mining, resources, mining, resources, mining. But it also tends to be, mining or resources companies, which is actually quite interesting. So saying that actually majority of stocks tend to have a very strong, mild to strong association with this component, and there's actually a few mining names which don't have actually an inverse relationship to that. All right, so I'm going to do the same thing for principal component 1 and principal component 2, and this is obviously, you get a bit more variability. Some are positive, some are negative. It's sort of a little bit harder to sort of interpret. If I actually go and reconstruct those factors based on, let's treat these values here as essentially weights. So if you can consider these as weights, if I actually were to go and reconstruct some of these, reconstruct these returns, what would actually come out? So this is what I'm doing here. All right, so if I actually go and look at, this is my market return. So this is the ASX. This is what the market done. If I look at PCA 0, this is what PCA 0. So majority of the time in finance, you tend to see that the first principal component, or PCA 0, tends to be exactly that, the market. And that was actually simply reconstructed by taking essentially the eigenvalue, sort of weight for each of those stocks, and multiplying it by their sort of respective return, and this is really what I come up with. If I do the same thing for sort of PCA 1, I get something like this, and this is where we come to a little bit of an issue, is that you try to intuitively assign a name to some of these principal components or sort of factors. I'm not really sure what the interpretation of this is. It could be sort of a momentum or something like that, but there's really no interpretation. It's just a mathematical construct. And you can sort of do the same thing for PCA 2. And the really nice thing is that you can sort of see, okay, well, I can actually construct a factor based on these principal components that really maybe suits various investment landscape. So maybe something might perform better during a turbulent time. So this purple PCA 1 actually did very well during that sort of COVID sell-off. Actually really sort of spiked up, and maybe PCA 2 is maybe something that's a little bit more tends to do well in pretty much all sort of situation. This is just sort of a scatter plot between the various sort of PCAs and market returns. We can have a little play in terms of, okay, well, what am I actually seeing here? What's the relationship between them? We can even do sort of a correlation matrix to see what the relationship is. So that's really it for this session. That was just a quick demo in terms of what is PCA, how do I actually apply it, and downloading some data, in this case ASX 200 data, understanding what the various PCAs are, what is an eigenvalue, and it's really just the weight or exposure to that principal component, and really reconstructing some of these principal components based on that decomposition. So if you'd like to join us in our next session, we will be covering clustering, which will really be a follow-on session from this. So we'll be using PCA into clustering. Thanks. Goodbye.